When we think about complex traits like, say, crop yield or maybe even human height, it's not just one gene calling the shots, is it?
No, absolutely not. It's usually a whole bunch of genes working together. Each adds a little bit, and sometimes they interact in, well, really complex ways.
Right, and figuring out which genes, where they are, and crucially, how they interact, that's the real puzzle for geneticists studying these polygenic traits.
It really is. So how do you map that whole landscape? How do you find all those pieces and see how they connect?
Well, that's exactly what we're diving into today. We're looking at a method built for this complexity, multiple interval mapping, or MIM.
And we've got some great material to work from here. This is based on the actual transcript and class notes from Professor Guilherme da Silva Pereira's statistical genetics course.
Yeah, from the Department of Agronomy at the Federal University of Viçosa, UFV. It gives us a fantastic insight into how these advanced methods are actually taught.
It really shows the evolution in thinking. The earlier methods, things like interval mapping, IM, or composite interval mapping, CIM, they were big steps, for sure.
But they mostly looked for one genetic region, one QTL at a time, right?
Exactly. It's just one at a time. And that caused some issues.
Like what kind of issues?
Well, if you had two QTLs really close together, these methods might just blur them into one effect. Or worse, sometimes point to a ghost QTL, a location that isn't actually real.
Hmm. And they couldn't really look for interactions between genes in different spots either, that epistasis thing.
Precisely. They weren't designed to directly search for or map epistasis. EMIM, on the other hand, was developed specifically to tackle that.
Okay, so its main goal is what? To look for lots of QTLs all at once.
Yes, exactly. To simultaneously search for and map multiple QTLs across the genome, and this is key to specifically identify and map the epistatic interactions between them.
All right, let's dig into that. So MIM basically builds a statistical model that assumes multiple QTLs are involved from the get-go. It tries to reflect that polygenic reality.
That's the fundamental idea, yeah. You're modeling the trait based on the combined effects of several genetic regions plus their interactions.
And you said that's the big leap, the epistasis part.
It really is. It's the first method we've talked about that directly builds testing for epistasis right into the mapping process itself. It's not just finding locations. It's starting to understand the genetic system.
Okay, I can imagine that modeling multiple locations and their interactions, that sounds computationally intense.
Oh, definitely. It involves some pretty sophisticated statistical models. The notes mentioned it's like modeling a mix of many normal distributions and complex algorithms.
What do these algorithms do?
Well, they have to search through tons of potential combinations of QTLs and interactions, figure out how well different models explain the data, optimize the positions and effects, estimate all the parameters. It's a multi-step process: searching, evaluating, optimizing, estimating, predicting.
And how do you know which model is best? You don't know the true number of QTLs beforehand.
That's the million-dollar question. The notes even call finding the absolute best model an unsolved problem in statistics. It's really tough.
So what do researchers do?
The goal isn't necessarily the perfect model, but a useful one. They use strategies like stepwise selection, adding or removing potential QTLs or interactions one step at a time, and criteria like AIC or BIC.
Right, those help balance how well the model fits against how complex it is.
Exactly. You want a good fit, but you don't want a model that's so complex it's just fitting random noise in your specific data set. You're aiming for predictive power.
The notes also mention something called orthogonal parameterization, like Cochrom's model. Sounds technical. Why is that important?
It's actually a really clever statistical trick for interpretation. Think about it. If you have multiple genes, maybe some are linked, maybe some interact strongly, how do you separate out the individual effect of gene A from the effect of gene B and from their interaction effect?
Okay, yeah, that sounds tricky. They could all be tangled up.
Right. Orthogonal parameterization sets up the math so that the estimate for each individual QTL effect and the estimate for each interaction effect are calculated independently of the others in the model.
So even if two genes are physically close or interact a lot, the model can give you sort of clean estimates for what each part is contributing. Their individual roles in the interaction role aren't confusing each other in the math.
That's the idea. It allows for a much clearer separation and interpretation of the different genetic effects. Additive, dominance, epistasis. You get a better picture of the underlying genetic architecture.
Okay, so let's recap the benefits. By looking at multiple QTLs and epistasis directly and separating the effects cleanly, what does MIME give you over the simpler methods?
Well, you generally get higher statistical power, More precision in locating the QTLs, especially when you do have multiple linked genes or interactions happening.
And that more complete picture of the genetic architecture, including mapping the interactions themselves.
Absolutely.
Yeah.
And that more complete model often leads to better prediction of trait values, which is super valuable for things like marker-assisted selection and breeding programs.
That Drosophila example in the notes was quite striking, wasn't it? How MIM could resolve what looked like one messy QTL peak in CIM into two distinct QTLs.
Yes, it really showed the improved resolution, and the fact that the model they built using MIM could predict that complex fly trait, the genital arch shape, with about 0.92 correlation. That's pretty impressive.
Wow. Yeah. Predicting something that specific with high accuracy just from the genetic markers really demonstrates the power of capturing those interactions.
It definitely highlights how much information is tied up in the way genes work together, not just individually.
So wrapping up, MOOM sounds like a really powerful, though computationally demanding tool. It lets us move past looking at genes one by one and tackle the real complexity of polygenic traits head on, especially those interactions, the epistasis, that simpler methods often miss.
It really does, and it makes you think.
Go on.
Well, if we know that most complex traits work this way, with networks of interacting genes, how much more are we likely to uncover about? Well, everything from disease risk to crop yield. If we consistently use tools like MIM that are actually designed to see that whole picture, the genes and their interactions all at once, what layers of genetic control are we still missing by not always looking for those connections?